Hello everyone and welcome back. We're in section 8.2, wrapping up this year with volume, and this is a new method called volume with cylindrical shells. So we're going to talk about in this video a recap of what we did last week, and I apologize to the Friday group in person that I was not there. I wasn't feeling too well on Friday, where I couldn't demonstrate the other method with limes, but hopefully this coming week I will be able to. But this method is called volume with shells. I'm going to do my best to help you visualize it. This one is really tricky, and that's why I think for the first assignment I want you to Google your own videos and find ways to help visualize this, and I'll do my best in this video as well. So the region we're going to cover in this one is, let's cover the region that's bounded by y equals root x, x equals 4, and y equals 0. Okay. And I'm going to demonstrate this volume here using what we did previously with this and washers, and then with this new method of shells. Okay, so y equals root x, x equals 4. That would put that at 2. So that looks something like this. Oops, kind of missed the line. Should be somewhere like that. Apologize. There you go. That's at 4, 2, and then y equals 0. So highlighting that region we're looking at is we're looking at this region right here. Okay. Now, previously, last week, we learned about discs, cylindrical discs, and washers. And let me cover how that works here. Okay, so if in the first one, let's do this first one, A, let's say we rotate about the y-axis. Okay, rotate about the y-axis here, and I'm going to quickly redraw this picture to help us see this. Should have given myself more room, but that's okay. So 4, 2, looks something like that. And we rotate about the y-axis. What we'll end up getting here is if we were to cut a cross section that's perpendicular to the line at which we're rotating. So we look at a rectangle there, an infinitely tiny rectangle, and we cut it, what we'll end up getting here is a washer, right? A very thin width. So if I draw it out here, well, to see it, is you get something that looks like this, which we would call a washer. Okay, and the volume of a washer is going to be the volume of the outer cylinder minus the volume of the inner cylinder. So outer cylinder minus the inner cylinder. And if you do the work, what you end up getting there is pi. I call the outside big R h minus the inside, which I'll call little r h. And then if you combine, if you notice that the pi and the height of this radius are both in common, the volume ends up becoming pi outside radius, didn't mean to draw the integral sign, pi outside radius squared minus your inside radius squared times the height. And then what's happening here is the height is a very small thickness, right? So that's your dx or dy. So in this problem, if we work it out so you can see it, your outside radius here, the distance from the center to the outside radius is just 4. So then your outside radius, so let me draw it down here. Your outside radius is 4. Your inside radius from the middle to that part of the rectangle, and again, there's my rectangle right there that got rotated around. Your inside radius, well, that changes depending on this function, so that's going to be square root of x. But since the thickness here is a very small cut and it's changing vertically, it's going to be in terms of y. So square root of x, we're going to write as y squared. So what ends up coming here is the volume is going to equal the integral from 0 to 2 as we fill this space vertically with washers from 0 up to 2 of pi times your outer radius squared minus your inner radius squared times your height of dy. Okay, and we can put this in a calculator. Of course, you can work it out by hand, and I encourage you to be able to work it out by hand. but to save time in this video, we'll just do it this way. And then that's pi times your outside radius squared minus your inside radius squared. Make sure I use the correct parentheses there. And then dx. And what I get there is 80.425 roughly units cubed. Okay. So that is rotating about the y-axis with, and I'll use a different color here, where your cross sections are perpendicular to your revolution. So in this case, we're revolving around the y-axis, and notice that our cuts were perpendicular to that. Now, what's this new method is we look at the same problem, but instead of cutting cuts perpendicular, it's going to be a slightly different cut. So what's new now is let's keep it rotating about the y-axis. But this time, if I draw the picture, draw it with a little bit more space. So 4 and at 2, you have our function root x. Is instead of cutting perpendicular, we're going to now cut parallel to the line of revolution. So now our cross sections are parallel to the line of revolution. And that's different. So instead of cutting it this way, we're going to cut small cuts this way. Okay. Now we're still revolving it around. So this is the visual part that gets a little bit tricky. Now, if I look at this entire region and I rotate that around, what I'll end up getting if I rotate this entire region around is what looks like a donut where it all concaves in towards the middle. Right, so the 3D shape here is something of a donut. But then all the inside is going towards a funnel-like middle. Now, how does it work if I take a cross-section that's parallel to the y-axis? Now, if I take a cross-section that's parallel and I rotate it around, what I'm going to end up getting here is what looks like a shell. All right, and that's what I say. It doesn't look like a shell at all. What is a shell? What I like to think about is like, we call it shells, but to me, what it looks like is a ring. Where, picture my wedding ring here. See if I can cut it. Where if we cut this and it rotates around, there's a small rectangle that you see here, and as it rotates about the y-axis, notice there's a lot of gap missing, very thin. Sorry, my finger's cutting that up, and it rotates around behind the paper and back. And that's just one cut, right? If we keep cutting this vertically, like if we cut one out here, parallel, well, then you just end up having a bigger ring. And now I don't want to get too confusing here. So how does that fill up the volume of this shape? Is the idea is, if you picture this ring, the volume of this ring, it's almost like there's a lot of rings here, and it's almost like sometimes I like to think of it as like an onion, where there's layers of rings. And these layers of rings fill this volume up from the inside out, rather than the washer method that we looked at previously. Okay, so if we picture this in this problem, so let's look at this one right here, some arbitrary value x. Okay, and let me draw it out here. So your cross section is, they call it a shell, but to me, it more so looks like a ring. That's my way of seeing it, Hein ring. So if I draw it, it looks something like this, where it looks like a cylinder, but it has a very, very thin space to it. So I'm just trying to help you visualize that there. Okay. Almost like the last roll on a paper towel in a way. And I guess this is almost like a roll of paper towels where what you're doing to fill volume is wrapping it around. A lot of wraparounds, rings of a paper towel. As you wrap those all up, it creates a volume rather than looking at cross sections perpendicular. So I guess you can think about that, something new. Put a question mark because it's a new idea. It's like a roll of paper towels. Roll of paper towels where each paper towel, wraps around the outside. So if we talk about that here, the volume, so what's the volume going to be? The volume is going to be made up of almost the surface area of this. I'm going to use the word shell because that's what they use, and then obviously times the depth of it. Now, if you think about a ring, if you unravel this, because we're talking about surface area, what you end up creating is a rectangular prism, right? So if you unravel it. Now, let's make sense of this. So the height of this shell, the height of this at this shell, notice that the height is changing and it changes with respect to x. So the height here is going to be root x. The depth is a very small change in x. So the depth here is going to be dx. So if I notice in my picture, the depth is dx, the height, put it over here, is root x. And then what's the length? Well, the length, if you imagine a ring, is the circumference of the circle. It's that distance all the way around there would be the length once you unravel it. So the circumference again is 2 pi times the radius. Now what's the radius of this? Well, the radius is the distance from the middle to wherever your cross section is, which was some arbitrary value x. So your radius here is going to be 2 pi x. So we put that all together, the volume is going to be the integral. Now we're going from 0 up to 2, or no, 0 to 4, because we're cutting parallel this way. So it's going from 0 to 4. Now we want the volume of all these. So let's see here. So the surface area, let me backtrack a little bit. Let's do it out here. The surface area of this, the outside surface area, is going to be 2 pi x times the height of square root of x. And if we want to find the volume of this shell or ring, again, I like to think about it as rings, well, that just adds in the depth, which is dx. So it's going to be 2 pi x square root of x dx. And if we add all these up, it'll fill in the volume like a roll of paper towels. So it's 0 to 4 of 2 pi x square root of x, because again, this is the volume of your ring or rectangular prism in a way, dx. And now notice, again, we should get the same thing we got in this one when we rotate about the y-axis, and we got 80.425. So let's check it here. What do we end up getting? Volume is going to be approximately, we put this in our calculator. So again, where does this come from? That's the length, the height, and the width of our rectangular prism, which is the shell unraveled. So here we go. Let's see if we get the same thing, and I hope we do. Math function integral 0 to 4 of, use new parentheses, 2 pi x times square root of x dx. And there we go. We got the same thing there, 80.425425 units cubed. And I can see at the end there it's slightly off. Not 100% sure why, but with what we're doing with 3 decimal places for the AP exam, we can see we get the same area. So there it is. This is the new thing, is creating shells, or I like to think about as rings, where the volume is created by finding the volume of these rings that spread outward and inward that fill up the volume, almost like a roll of paper towels, which is slightly different. And you do that by doing cross sections parallel, which is slightly different than doing cross sections perpendicular, which is washers that fill up the space in a more concrete way. Okay, So that's the first video on this. I again encourage you to look this up to find visuals online. In the next video, we'll look at maybe one rotated about the x-axis and why this method is even needed. Okay, hope that helps. All right, good luck and bye-bye.